In this video I want to describe in detail the components of a trafficking vesicle. And I want to focus on the sandwich that exists between the membrane and the coat, the components that are going to be in this part. I also notice we'll move on to a more detailed diagram in a second, but notice that there's a coat here and not one here. That coat has got to be gone before this step can occur, the fusion reaction. So there's an uncoating event that we have to account for. And then notice that fusion occurs with an intermediate that kind of looks like this. And the significance of that is that this process is actually potentially reversible. That is, there is a fail-safe mechanism built into the overall process that if this vesicle bumps into the wrong target membrane, and we'll talk about how that determination is made, it is allowed to float away before the terminal irreversible step of fusion occurs. So we'll go into the details of this process a little bit, beginning with the cargo, the red and the green, and then talk about what's in here and not shown on this diagram. So that is what's going on here. So this is a vesicle. It has been formed by the complete budding off of that coated pit, which is sometimes called the coated bud, so that the coat does form a complete spherical shell around trafficking vesicles. It's actually not always spherical. Sometimes it has other shapes, but in any case, it completely encircles the trafficking vesicle at an early stage in the overall trafficking reaction. And that process is followed sooner or later by uncoating, either partial or complete, to get the trafficking vesicle that is prepared for fusion. Okay, so let's go with the cargo. So here's the soluble cargo that we've been dealing with that, again, started out as green in the co-translational translocation. This could be collagen, for example, something that's going to be exported into the extracellular matrix. And then we have the green things that are, in this color scheme, integral membrane proteins that are destined to exist on some membrane system, maybe the plasma membrane, but they could also be on the Golgi, or they could be on the ER membrane, things like that. So to try to make that point, I tried to make this a little bit more specific. If you don't know what this is already, you will pretty soon. This is a G protein coupled receptor, kind of a very iconic shape. So this is a very common transmembrane cargo that we would encounter. This is the S protein of the coronavirus that I'll talk about in terms of its very bizarre trafficking reactions once we get to the point of doing that. And this is just a generic integral membrane protein. Never mind what the blue thing is for now. So here's a soluble cargo, but look what's going on here. So in this case, there is something in yellow to distinguish it from the cargo that is interacting with the cargo and also is plugged across the membrane. So generically, this would be referred to as a cargo receptor, because it is doing exactly what that name indicates. Okay, so once we introduce the concept of cargo receptor, it's time to start talking about the blue thing. And the sandwich that I mentioned, the coat is here, the vesicle membrane is here, and it's this bilayer, pretty standard looking membrane. So this protein, and this protein, this protein, and this protein, there are different shapes, and the idea is that this is a function that is accomplished by a family of proteins that collectively are referred to as adapter proteins. So the things in blue on this diagram are collectively referred to as that. And sometimes they are given the designation AP and then a number, but not always, so we won't worry about that just yet. But in any case, the term, I think, is pretty obvious. What they're serving as is an adapter between the cargo, either directly, if it's a transmembrane protein, or indirectly through a cargo receptor, and the coat. So this adapter protein would be specific for a particular coat, meaning clathrin versus COP1 versus COP2. So depending on which trafficking reaction we're talking about, that would dictate which type of adapter proteins. But adapter proteins are going to be in all of them in one form or other, doing essentially the same job. Not always the same way, but they are serving as the bridge between the coat and the cargo. So this is one mechanism that definitely is involved in the specificity of the reaction, because ultimately it's the joint decision between the cargo receptor, if there is one, there wouldn't be one here, and the adapter proteins that are going to say, yeah, this is a mechanism that needs to get us to the Golgi or wherever it needs to go. So adapter proteins are going to be present in this sandwich, and notice that once the coat's gone, they're still there because they are associated with either the cargo as a membrane protein or the cargo receptor. Okay, so there's that. How about these things in brown? So you can't see it at this level of resolution, but if we zoom in, then there's a hint. There's going to be a letter T on all of these at this stage in the overall process, and I'll go ahead and show you that over here it's a D. So I'm hoping that triggers some recognition in your head. But the fact of the matter is that these things are small G proteins. It is, once again, a family of G proteins, most of which are referred to or abbreviated as ARF. Never mind what that stands for. It doesn't help you at all to memorize or tell you what they do. But in most particular trafficking reactions, it is these small G proteins, and they are G switch proteins, meaning they undergo that series of on and off reactions that are controlled by GEFs and GAPs that I talked about way back when. They are associated with the budding process and the specificity. That is, they are instrumental in saying, oh, you're here, then we need to bring in this coat. So they oversee that reaction, but also, and they do that in the GTP bound form, but also they are, in most cases, the timer for the uncoating reaction. So how long this particular reaction takes, 1 second, 10 seconds, a minute, that's going to be determined by the rate of GTP hydrolysis on the small G proteins in brown. And the process of timing that is the standard G-switch process. Okay, so that's the ARFs. Now, let's say they have done their job more or less completely, and the trafficking vesicle is uncoated. So whatever it was, COP1, COP2, clathrin, has been disassembled into monomers and then probably reassembled on some other trafficking vesicles somewhere else. So what you have now is an exposed bilayer with no coat, and that exposure is critical, obviously, for the fusion that's going to come next. So that process, in order, is going to involve two additional components. The first is another blob that's about the same size as this, and I hope that's a clue. It's going to be another type of G protein called RAB. And RAB is a term that specifies a very large family of small G proteins, G-switch proteins, that start out in this overall process on this reaction as cytoplasmic soluble entities. Once they encounter the appropriate uncoated trafficking vesicle, they're going to associate with the cytofacial side of the trafficking vesicle and supervise the next step, which is the fusion reaction. And I'll talk about that in detail before too long. So this thing is going to end up tightly associated with the plasma membrane here and be part of the specificity of that overall process. So I mentioned that this is a large family of proteins, and what I mean by that is that there are many types of RABs, and the advantage of that sort of idea, having a family of proteins like this, is that you can use those to determine the specificity of the fusion reaction. So here is a short list. The family is much bigger than this, actually. But for example, if we're talking about what we've been calling anterograde, the COP2 vesicular traffic from the ER to the Golgi, then if that's the direction that we're going, then this RAB would be RAB1. But if it's going in the opposite direction, Golgi to ER, then it would be a different RAB, maybe RAB6. And we'll see how that distinction can determine specificity of the actual fusion reaction before too long. But before doing that, what I wanted to point out is what I think is the final component of this cartoon, and that is these light blue entities. Notice that they're actually here but covered by the coat. We're going to need those for the fusion reaction. These would be at this particular location would be referred to as V snares. That are going to be part of the mechanism that allows for the fusion, but also one of the components of the specificity of the fusion, such that V snares have got to be paired with the appropriate target snares, so-called T snares, in order for the fusion reaction to be allowed to proceed.